What if the largest object in the universe isn't a supercluster, isn't a galaxy wall, isn't even made of matter at all? What if the biggest thing out there is an absence so wide that light can spend hundreds of millions of years crossing it, and still find almost nothing inside? Because, if that's true, then the universe isn't mostly made of stuff. It's mostly made of distance, of emptiness. And that changes the meaning of every map we've ever drawn of the cosmos. Tonight, let's ask the question the right way. Not, what's the biggest structure? But, what's the biggest presence in the universe? By volume. And what does that presence do to everything that tries to exist inside it? In the late 1970 seconds and early 1980 seconds, astronomers were doing something brutal and simple. They weren't photographing beauty. They were counting. Galaxy after galaxy. Position after position. Redshift after redshift. And when they began plotting those distances in new ways, something unsettling appeared. Not a new cluster. Not a new constellation of galaxies. A blank region. A place where, statistically, galaxies should have been, but weren't. At first, people resisted it, because the old assumption felt safe. On the largest scales, the universe should look smooth, homogeneous, same average everywhere if you zoom out far enough. But the data didn't feel smooth. It felt wounded, like the universe had missing pieces. And one of the most famous early examples became the Botess Void, a region so underpopulated it earned a nickname that sounds like folklore. A Great Nothing. Roughly 330 million light-years in radius, with far fewer galaxies than expected. That wasn't just big. That was a new category of reality. Now, if you ask most people what the biggest thing is, they'll point to the giants made of matter. Superclusters. Enormous collections of galaxy groups and clusters, stretched along filaments like beads on cosmic threads. Our Milky Way sits in a vast neighborhood often described through the lens of Laniakea, a mapped basin of attraction in the local universe, spanning hundreds of millions of light-years and containing on the order of 100,000 galaxies. Superclusters feel like the correct answer because they are bright. They announce themselves. They look like structure. They look like power. But here's the quiet trap. Even the grandest luminous structures are minority by volume. They're the glittering knots, not the fabric, not the space between. If you could step back far enough, the cosmic web doesn't look like a filled universe. It looks like a universe that has been stretched thin, until most of it is nearly empty. This is where the story flips. Because the largest objects, in a certain sense, are not clusters. They're voids. Vast, underdense regions between filaments and walls. The dark gulfs that make the bright parts look connected. They're difficult to see for the same reason you can't photograph silence. You detect them by what fails to appear. A working definition often used in cosmology is that voids are regions whose density is far below average, commonly described as less than about 10% of the mean in terms of galaxy number density, though practical thresholds vary depending on method and data. Let that sink in. The average density of the universe is already unimaginably thin, and voids are thinner still. In the deep interior of a void, you can be millions of light-years from any major galaxy. No spiral arms overhead, no nearby star fields, just the faint microwave afterglow of the Big Bang, and a darkness that isn't dramatic. It's indifferent. And here's the key. Superclusters are impressive because they contain a lot of mass. Voids are terrifying because they contain most of the volume. So when you ask, what's the biggest thing? The honest answer may be, the biggest thing is the nothing that surrounds everything. Now we need to be careful with language, because void doesn't mean a perfect vacuum. Even in the loneliest regions, there's still a trace of gas, a drizzle of particles, cosmic rays passing like distant sparks, and the persistent glow of the cosmic microwave background. But compared to galaxies and clusters, voids are radically simple, and that simplicity makes them powerful. Because the cosmic web is not built only from what shines, It's scaffolded by dark matter, a dominant mass component that shapes structure through gravity, even though it doesn't emit light. Where dark matter density is higher, filaments and clusters grow. Where it is lower, voids open wider. And then there's the second invisible player: dark energy. The accelerated expansion of the universe, first recognized in the late 1990 seconds, acts like a kind of repulsive effect on the largest scales. In dense regions, gravity can fight back. In voids, matter is sparse. So dark energy's influence becomes cleaner, more dominant in practice. Which means the emptiest regions are not just passive gaps. They are the places where the universe's expansion can feel most like it has room to take over. A strange irony. The emptier the region, the more it can become a stage where the universe's future is decided. For a long time, voids were treated as awkward leftovers. The bright stuff was the real subject. The empty space was what you ignored. But modern cosmology learned a humbling lesson. The universe's structure is not just clusters scattered in space. It's a network, a web, and voids aren't just single holes. They can form hierarchies, like nested chambers in a cave system. In fact, void-finding techniques often borrow from a concept called a watershed approach, a way to define basins and boundaries based on how flow would move through a landscape. It's a beautiful idea. Treat dense filaments like ridgelines. Treat underdense regions like valleys. Then let the math identify the basins. The voids, as coherent regions defined by the surrounding topology. This approach has powered public void catalogs built from surveys like the Sloan Digital Sky Survey, using watershed-style algorithms such as Zobov and its descendants. And when you do that, the universe reveals something eerie. Inside big voids, there can be faint filaments. Inside those filaments, smaller knots. And between them, subvoids. Voids within voids. A kind of cosmic nesting. Not infinite, but suggestive. As if the universe keeps repeating the same language, just at different volumes. Here's where the story stops being just poetic and becomes scientifically tense. Because cosmology relies on a deep assumption that on sufficiently large scales, the universe is statistically uniform, clumpy close-up, but smooth far away. A commonly cited scale of homogeneity is on the order of hundreds of millions of light-years, often described around to 300 million light-years when averaged appropriately. And then, supervoids enter the conversation. Some propose supervoids appear so large that they rub against that expectation, raising the question: are these simply rare statistical extremes? Or are they evidence that our models are missing something? One famous mystery tied to this idea is the CMB cold spot, a region in the cosmic microwave background that seems unusually cold and unusually large. One leading class of explanations suggests that, in that direction, we may be looking through an extended underdensity, an Eridanus supervoid, or a connected system of voids, which could imprint a temperature decrement through effects like the integrated Sachs-Wolf mechanism. But the situation is not clean. Research finds evidence for underdensities aligned with the cold spot, while also arguing that even an elongated supervoid may be insufficient to fully explain the observed cold spot pattern on its own. And then there's another disputed idea: a local giant void around us, sometimes discussed in relation to Hubble constant tensions, with ongoing debate about evidence and interpretation. This is not settled territory. But that's the point. Voids are no longer leftovers. They're now one of the places where cosmology gets tested the hardest. Because if the emptiest structures are too big, then the universe's smoothness might be less simple than we thought. Here's what makes this moment different from the 1980 seconds. Back then, voids were discovered like accidents, like someone turned a corner in the data and found a hole in the wall. Today, we are building instruments designed to map the universe so broadly that voids can't hide. The European Space Agency's Euclid mission launched the 1st of July 2023 to map the large-scale structure and help constrain dark matter, dark energy, and gravity, covering roughly a third of the sky and probing out to around 10 billion light-years. NASA's Nancy Grace Roman Space Telescope is assembled and moving toward launch. NASA states it is slated by May 2027, with the team tracking for as early as fall 2026, with major survey capabilities aimed at dark energy and cosmic structure. This is the new era. Not just finding galaxies, but mapping the dark geometry between them, because voids may be among our cleanest laboratories for the universe's deepest ingredients. Galaxies are messy. They are full of feedback, star formation, magnetic fields, explosions, chemistry. Voids are comparatively quiet. That quiet preserves information. And if dark energy is a property of space itself, then the most space-dominated regions, the voids, may be where its fingerprint is easiest to read. So when you ask what the biggest thing is, you're not just asking a trivia question. You're asking what the universe is mostly made of. And the universe's answer is unsettling. It's not mostly galaxies. It's not mostly stars. It's not mostly light. It's mostly the space where nothing holds. If this changed the way you picture the universe, hold on to that feeling the next time you look at the night sky. Because what you're seeing isn't the universe filled. It's the universe threaded, with most of reality hiding in the dark gaps between the threads. And if you want to keep going, we'll keep mapping the places the light doesn't reach, until the silence starts to explain itself. The universe doesn't surround us with wonders. It surrounds us with emptiness. And somehow, we learn to call that home.